In the last section, we have seen how to calculate the gradient of a function for any point A lying on the graph. Since we can do that for any point lying on the graph, this means for any value of x, this gradient becomes actually a function of its own. And we call this function f dash of x, or also f prime of x. And the f dash of x is then just the limit of delta x going to 0 of f of x plus delta x minus f of x divided by delta x. You remember before we just said the gradient is at some point x0 was f of x0 plus delta x minus f of x0 divided by delta x, and now we say this is just for any value x0, so for any value x this becomes a function. We call this the derivative function, or the derivative of f. So let us look at the first example where f is given as y equals x to the power of 3 minus 2x. So we want to find the derivative f dash of x. Let me copy just the definition from up there. Limit of delta x going towards 0 of f of x plus delta x minus f of x divided by delta x. So now let's insert into the function given up here. So this means x plus delta x to the power of 3 minus 2 times x plus delta x. This is the f of x plus delta x, I've put it in cornered brackets, minus f of x, which is then just x to the power of 3 minus 2x, and the whole thing divided by delta x. And now let me expand this whole expression, and it becomes now quite long. So you have more space than I have. So x plus delta x to the power of 3. If you remember the formula for that, or you can use the Pascal triangle or calculate it explicitly, well, what we get is x to the power of 3 plus 3 times x times delta x plus 3 times x squared plus delta x plus 3 times x times delta x squared plus delta x to the power of 3. Oh, here the bracket was not closed. Minus 2x minus 2 delta x. And here we still have minus x to the power of 3, and this becomes plus 2x here, divided by delta x. So we see that the x to the power of 3, they cancel out. And what we get now, also the 2x here, minus 2x plus 2x cancel out. So maybe let's mark it, that makes more sense. X to the power of 3 cancels out. The delta x, the x here cancels out. So we see what remains always has a delta x as a factor in the sum. So we factor out the delta x, and what remains is in the bracket. So we have delta x times 3x squared plus 3x delta x plus delta x to the power of 2 minus 2. The whole thing divided by delta x still. Now we can cancel out the delta x, and what remains is now limit delta x going towards 0 of 3x squared plus 3x times delta x plus delta x squared minus 2. And now we see this here, this goes to 0 because the x goes to 0, the delta x I wanted to say, this one also goes to 0. So what remains in the end is just 3x squared minus 2. Now we have found this derivative function of the function f. So Now we can find also the value of f dash at any point x0 of this function. So let's look at example 2. We want to find the value of f dash of 2, which means we have this function f here. This is the same one as up here. So we know f dash of x is this. So f dash of 2, that's what we're being asked for. We get that just by inserting into the function equation. So we get 3 times 2 squared minus 2. Inserting it here, which means we get f dash is 10 dash of 2. The same for f dash of 5. We insert 3 times 5 squared minus 2, and we get 73. Next task now is find the gradient of this graph of f, and again it's the same function here. Find its gradient at the point with x coordinate minus 2. Well, that's exactly the f dash of minus 2. So again, we can insert 3 times minus 2 squared minus 2, and we see we get the same like we had before, the 10. Another example, here we want to find the rate of change of the function f, the same one still, with respect to x, the change of rate at x0 having the value 3. Again, we can just use our f dash that we found. What we want is f dash of 3. So insert the 3, we get 3 times 3 squared minus 2. So we get the rate of change is 25 at x0 equals 3. There are some alternative notations for this f dash, for the derivative function f dash. We can also just write, since y is f of x, we can just write y dash. Or another way of writing that is just, instead of writing y dash, dy by dx. This dy by dx represents actually the fraction delta y by delta x when delta x goes to 0. So this dx means delta x very, very small going towards 0, and dy, well, when delta x goes to 0, then also the delta y becomes very, very small. So we write dy by dx. And just remember, delta y divided by delta x is the gradient of this line through a and b. And when x goes towards 0, then this delta y divided by delta x is then this dy by dx is then just the gradient of the tangent. So that's why it makes sense to use this notation. Dy by dx is then just this limit, so f dash of x. So in example 5, find for this function the y dash. Well, the y dash is just the same thing like f dash of x. We calculated that before, so we have just 3x squared minus 2. And the same thing virtually applies to example 6. We want to find dy by dx of this function here. So dy by dx is the same like f dash of x, which we calculated already. So 3x squared minus 2 again. So we should note that for some function f, for any function f, the following expressions and interpretations, they always yield the same result. So when we ask for the rate of change of f at some location x equals x0, when we ask for the gradient of the tangent to the graph of f at some location x equals x0, that's the same like the rate of the change. The gradient of the graph of f at the location x equals x0, Well, that's the same like the gradient of the tangent by definition. When we say we want to know the differential quotient of f at location x equals x0, or when we say we want to know the derivative of f at location x equals x0, and we can always write that just as f dash of x0, or as we said before, the y dash at x0, or dy by dx at x0. Finding the derivative by using the differential quotient, as we did for this function y equals x to the power of 3 minus 2x up here, this here, we did here, this is called differentiation from first principles. So let's now look at a few more examples. In example 7, we're given a function f, and we should find the points where this function f has the gradient minus 3. We're being asked for the gradient. This means we'll have to look at the derivative function. Let's start by rewriting this function y equals x plus 12 divided by x in a little bit a simpler form by taking the fractions apart as two fractions and simplifying it. We get y equals 1 plus 12 divided by x. So now to find the derivative function, we use just the definition, which just says f dash of x is this limit here. And in a first step, we just insert f of x plus delta x and f of x using this here. So what we get is this here, just by inserting x plus delta x in this equation, we get here the first bracket, and then just for the x, we get just a copy of this in the second bracket. Now, simplifying this, or expanding the brackets, we see the 1 and the 1 here. These two ones, since there is a minus, they cancel out. What remains is this here. So now let us expand this. And we get to have the common denominator. It's just the product of these two. So we have to expand 12 by x and the 12 here by x plus delta x. Then let us get the delta x out of here, the double fraction, so we have to multiply its reciprocal value, which means times the 1 divided by delta x to get it back here. And here we expand now this, so we get minus 12x minus 12 delta x. Obviously, the 12x cancel out. And then next step, let's rewrite that, and we see we can cancel out the delta x now here, and what remains is the limit of delta x going towards 0 of minus 12 divided by x plus delta x times x. The delta x, since goes to 0, obviously, since delta x goes to 0. So what remains in the end is just minus 12 divided by x squared. So this is my derivative function. And now we have just to find where is the derivative function equal to minus 3, because the derivative function tells us the gradient. So we want f dash of x to be equal to minus 3. So minus 12 divided by x squared should be equal to minus 3. So let's multiply with x squared and divide by minus 3. And we get 4 equals x squared, which means taking the root, x1 and x2 are plus and minus 2. We need now to find also the y values. So if x1 is 2, then we have y1 is 1 plus 12 divided by 2. So we get 7. For x2 being minus 2, we get y2 is 1 plus 12 divided by minus 2, which means 1 plus minus 6, so we get minus 5. And so the 2 points that we were looking for are 2, 7, and -2, -5. So these are the final results for example 7. We didn't know before how many points we would get. We found out there are 2. Now try example 8 on your own, even though it's a little difficult. And stop the film, and here comes the solution. Y dash just means f dash of x, and f dash of x, we can use the differential quotient, this definition, which means this limit here. And now let us insert for f of x plus delta x and f of x, and we get this expression here. And to solve that, what we have to do is to get the two fractions on make one common fraction from that. This means the common denominator is just the product of the two, so we have to expand here by square root of x and here by square root of x plus delta x, and we get this expression here. In the next step, let's get rid of this compound fraction. So let's multiply this denominator with the reciprocal value of this. This means with 1 divided by delta x. So we get this expression here. This is the original numerator here, and now times 1 divided by delta x. And what is disturbing here is this square root of x minus square root of x plus delta x. We cannot really work with that. So the idea is to use the third binomial formula. So we expand by square root of x plus square root of x plus delta x. And now when we multiply this times this using the third binomial formula, we get x minus x plus delta x. We get this times this, so this squared a minus b times a plus b is a squared, so square root of x squared is x, minus b squared, square root of x plus delta x squared is x plus delta x. And the denominator is just the product of all these factors here. Now we see this simplifies, the x cancels out, so what will remain is minus delta x. And we can now factor out the delta x, cancel out the delta x here. So what remains is minus 1. And what happens, the delta x here goes to 0. This delta x goes as well to 0. So we see we get minus 1 times the square root of x here times the square root of x here, and this is square root plus x plus square root of x, so times 2 square root of x. So the final result that we get is minus 1 divided by 2x square root of x. In example 9, we're going to look at the graph of the function y equals 1/4 x squared, and this time we're not going to find the derivative by calculation, but we want to argue graphically, and that's a preparation for the next section. So we want, here the graph is shown of f, and also the tangents. Some tangents are drawn, namely the tangents in the point with x coordinate 4 and in the point with x coordinate -2. And so we want now to read off graphically the values f dash of -4, f dash of -2, and so on. Let us start with f dash of -2. This means the gradient of the curve in the point with x coordinate -2. So in this point here, the gradient of the curve here corresponds to the gradient of the tangent here, and we can read that off now directly. F dash of -2, that's the gradient of this tangent 1, and that's 1. Sorry, -1, obviously. We go one to the right and 1 down to stay on the graph. Now, for symmetry reasons, we know how much f dash of 2 is. F dash of 2, this means it's the gradient in the point with x coordinate 2, so x coordinate 2, so we're in this point, and because we know that fy 1/4 x squared is symmetric about the y-axis, so the tangent here will be exactly the same, or no, the tangent is the T1 mirrored at the y-axis, and this means its gradient is now not -1 but +1. Then the f dash of 0, so the gradient of the point of the tangent in the point with x coordinate 0, it's this point here. Well, obviously the tangent here is just the x-axis, so the gradient of the x-axis is 0. Let's look at f dash of 4. That's also asked. Well, here we have x coordinate 4. This is this point here. The tangent is drawn, so we can read off the gradient. Well, here we have 1 point, we go 2 to the right and 4 up to get back on the line. So this means we have 4 divided by 2, so the gradient is just 2. And now with the same argument as before, to find the gradient in the point with x coordinate -4, this means here, well, that's this tangent is just this tangent mirrored at the y-axis, which means it has just the same gradient as the other tangent but with a different sign, so it is -2. So we found now these f dash values, these gradient values for the different x values here. And now we want to draw the graph of f dash, which means we have to find points that lie on the graph of f dash. So this point, this yields 1 point, namely the f dash, the argument is -2, and the y value, the function value of f dash here is -1. Here we have argument 2 and the f dash is 1. Argument is 0 and f dash is 0. Here we have 4 and 2, and the last one is -4 and -2. So now these are all points. All points lie on the graph of f dash. So let's draw them. -4, -2, 4, 2, 0, 0, 2, 1, -2, -1. And we see all these points just lie on one line. So this graph is just, the graph of f dash is just a straight line.